Good afternoon, and welcome to the session titled Geothermal Borefield, Horizontal Piping Design Operations. My name is John Rath. I'm Director of Operations for NY-GEO. It's good to see everybody come in. This is going to be a great session, so make yourself comfortable. A couple things about the logistics of it. I know a lot of folks are here for credits and PDHs. So the way we're going to work that is at the conclusion, I need you to come up here at this table. I've got some sheets laid out. Some of them I'll have names on them for those of you that have pre-registered for the credits, and I just need a signature. If you haven't registered for the credits, I've got a blank sheet where I need to get some information from you, and then you need to go down to our registration table and take care of the fees and things for that. Certificates will come in the mail in probably a month. So we'll work that out toward the end. Today's a wonderful panel. We've got some outstanding speakers, and we've got a very important moderator. Her name is Tracey Ogden. She is the Vice President of Drilling for Brightcore Energy. One of our big supporters in NY-GEO, as many of you are. So I'm not going to belabor or take time. I'm going to turn it right over to Tracey because we've got a really impactful session. Please help me welcome Tracey Ogden from Brightcore.
Sure. Thank you, John. Everyone just take a seat, and I just want to say I'm very excited to be here today. We have a really exciting topic to discuss, and we have a pretty amazing panel here. We have 3 amazing panelists, subject matter experts. Today we're going to discuss the horizontal piping design, some of the different strategies that are being implemented currently throughout our industry. We're going to introduce some things that are a little bit different. First and foremost, we have Kim Ojanne from Rototec. He will be discussing some of the European methods. He will be our first panelist. We also have Stuart Lyle. He comes from ISCO Industries. He will be talking about the traditional reverse returns and the volts that we typically use. And we also have Jens Ponikau, who will be talking about something a little bit different, something that we do within the piping design that's not is utilized as much, but it's something I think it's important for us to all to start to realize there's different technologies out there. So our intent is to show you some different technologies, and hopefully you walk away with a better understanding. So without further ado, I'm going to bring up Kim Ojanne from Rototec. I know there's going to be a lot of questions. I ask that you save the questions for the end of the presentation, and we'll get to each and every one of you because I'm sure there's going to be a lot of interest in this topic. Thank you for coming here today, and I hope you're enjoying NY-GEO.
Thank you, Tracey, and thank you for having me here today. For those of you who don't know who I am, my name is Kim Ojanne, and I work for a company called Rototec. We're a geothermal drilling company. We've been doing geothermal drillings in Europe since 2007, and we started to drill in US in 2023. So I've been in US for 2 years now. So today I'm going to compare a little bit of what I've seen in Sweden and what I've seen in US. So in the Nordic countries, Sweden, Norway, Finland, we're drilling a lot of boreholes. Then we have operations in USA on the northeast mostly, and in Germany. So we operate 66 drilling units, and we drill roughly 6.5 million feet per year. So we're going to compare the reverse return headers and what we do in Europe. So geothermal energy systems require efficient underground pipe connections. And the choice of header system affect cost, performance, and accessibility. And this is one of the points that I think is really important to discuss today, or what I at least want to present. So this presentation compares Swedish and American practices for manifold systems. And then we have some objectives for this, and it's to examine how the choice of header systems affects costs, performance, and accessibility, and learn the similarities between and differences between Swedish and American practices for manifold systems. So, the Swedish common practice, we use manifold vaults, or sometimes we also have manifolds inside the building, or manifold cabinets on a parking lot. Let's see if this laser works. So these are the manifold chambers or manifold vaults that we use. Then we have boreholes, and as you can see, the individual boreholes are connected to these, I would say, quite small manifold vaults. And the pipes running from the borehole are pre-insulated pipes, so there's no transfer between the cold and the warm pipe, so to say. And then from the manifold vault, we have the main pipes running. So you can connect this manifold chamber. You could have a second manifold chamber here and a group of boreholes up here, and then you can have the main lines run. You can have a T connection here, or have the main lines to run through the manifold chamber. And each vault contains a small manifold that's inside the vault. So this is how it looks like in Sweden. And also, little bit interesting to mention, we use DR17 pipes, which is very thin compared to, in US mostly we have DR11 pipes. I don't say we can use DR17 because in the Nordic countries we don't grout, which might sound crazy, but I guess we're not as concerned about our groundwater. We do grout when we are in water protected areas, groundwater protected areas. The vertical loops typically are close to 1.4 inch, 1.56, 1.74 in diameter. Because we have thinner walls, we can also do bigger loops. And then with the pre-insulation, they're a little bit bigger, like 2.5, 3 inch, 3.5. So this is the tubulite insulation, and there's a plastic cover on top of it. And then we typically run the main lines, can be 3 inch, 3.5, 4.3, 6.3. Of course, it can be even bigger if you're doing installations for hundreds of boreholes. These main lines will become bigger. And we're typically using electrofusion. Butt fusion, socket fusion, very rare to see in the Nordic countries. And this is a manifold cabinet, so either we have the vaults or we have this inside the building. This is an example design with multiple manifold chambers. This drawing actually shows a lot of things. So let's start. This is a borehole. This borehole is angled, so it goes in this direction. The bottom of the borehole theoretically is here. And the circle here is where it takes up energy, so to say. So we do a lot of angle drilling, and then we have the boreholes. These are 1, 2, 3, 4, 5, 6, 7, 8, 9 boreholes going into this manifold chamber. And then we have a bunch of boreholes going into this manifold chamber. Then we have the main lines running here, and it's a T connection here. So we have 2 manifold chambers coming in, and then 2 pipes into the building. This makes, for me, a lot of sense if you're in an urban area where you don't have a lot of space running the reverse return header systems, or you don't have the space to do all the trenches. So this is a little bit simpler way of doing it, I would say. The US common practice is reverse return header systems. This is from a project we've been doing at UMass Amherst. It requires equal pipe lengths ensured to balance flow across all boreholes. Manifold may be large and complex due to long pipe runs, and locations of vault can be centralized, big vault or inside, outside, or internal manifold inside the technical room. Overview of design philosophies, manifold chambers versus reverse return header. I would focus on a few things. It's easier to balance individual wells. We have balancing valves for each individual loop, and if you have trouble with a loop, you can shut off just that one loop that you're having trouble with instead of closing the whole circuit. And of course, maybe one of the not so good things is that you have multiple manifold vaults if you're doing the Swedish way of doing it. So instead of having one big manifold vault, you might have 5 manifold vaults. So depends on what makes most sense for the project you're on at the moment. So I listed pros and cons. Possibility to control the flow and maintain a stable flow through each borehole for the Swedish version. Possibility to shut off individual boreholes in case of leaks. If you have a leak on a reverse return header, it takes time to find where the leak is. So because like 10 boreholes or 8 boreholes is connected to one circuit. Easier to get rid of microbubbles. So when we flush one loop with the horizontal pipe, it's easy to get out the microbubbles. Easier installation per borehole group, less excavating, and better suited for dense urban installations. And the cons are underground manifolds can be difficult to access for maintenance. And the pros with the US version is equal flow distribution, centralized control and maintenance, lower pressure drop, and less pumping power needed for normal operation. Complex design and installation, more vulnerable to single point failures. So again, 2 different solutions. I think we talked about this possibility to shut off single boreholes, easy to get rid of microbubbles with these manifold vaults, and we can use motorized valves. It's possible to customize the flow through the boreholes, for example, temperature gradients in borehole thermal energy storage BTES systems. If you, for example, want a higher temperature in the middle of the system, so you can use those motorized valves. Yes. So what should I answer these questions or the audience? Okay. Questions. What are the primary differences between Swedish and American horizontal piping design? I'll go to the next slide where I have the answers. Both systems aim to ensure efficient geothermal heat transfer. What does the choice of horizontal design depend on? The choice depends on project scale, regulation, space availability, and installer preference. What does Sweden prioritize in its designs, and what does the US prioritize in its designs? Sweden prioritizes modularity and simplicity, whereas the US leans towards centralized and engineered balance. That's my presentation.
just a couple of brief comments before we bring up Stuart Lyle from ISCO. I'm not sure if anyone in the audience had picked up on a couple of vast differences from Sweden to the US. A couple of things that I picked up were just the sheer size of the pipe, right? And from going from an SDR11 or an SDR9 for the loops to an SDR17. So those are some design considerations we need to think about, as well as the way that we were fusing the pipe. In Sweden, they were discussing doing electrofusion. Here in the US, we typically, as engineers, we would typically have to let you know where there was electrofusion and in essence, ask for permission. Here in the US, we typically land on the button socket fusion. So these are some of the differences that I just wanted to highlight in case you didn't pick up on it in his presentation. Next, we're gonna have Stuart Lyle from ISCO Industries.
My name is Stuart Lyle. I'm the Geothermal Sales Director for ISCO Industries. I've been in the geothermal industry for close to 2 decades. I started out as a driller, looping and grouting, manifolding, got into project management, and now I lead the geothermal sales team at ISCO. Essentially, I do a lot of educational lunch and learns around the country with engineer firms, design firms, and try to share this information. So although what I'm going to give you is very brief today, keep that in mind. If you have an opportunity where you would like to learn more, kind of a deeper dive into this information, please reach out to me. I'll be more than happy to come to your facility, your office, or your job site, and be able to convey some more detailed information to you. All right. So the learning objectives here for my presentation: learn how vaults can reduce piping penetrations at the building, discover how balancing valves can work with reverse return piping to help balance your design, and then understand how a bypass can separate your piping scopes. A couple of things I want to point out with the pictures here. In the upper left-hand corner, that is a geothermal vault for a large system in Pahrump, Nevada. This is for an elementary school, but you can see this is a full-size vault. All the supply and return pipes coming into it. To the right of that is a balancing valve, which goes on your reverse circuit inside the building. And then at the bottom, this is essentially a very large mechanical room that shows you all the penetrations coming up through the footing or the floor. All right, so to design to reduce penetrations in excavation, by consolidating and manifolding your circuit supply and return piping at a vault, you can reduce the number of piping penetrations and excavation to the mechanical room. Less is more when it comes to creating space. This is a recent example of a project I'm working on currently. If you look at the top, you see all your circuit piping in purple or blue. I'm a bit colorblind, so the blue or the purple color there. That's actually running across a road or running under a road. So you see where the arrows are, that's an existing road. You have your piping penetrations that bore under the road and then come into the building there. This is a prime example where a vault would be very useful. Essentially, you could reduce the number of directional bores under that road by incorporating a geothermal vault and only having 2 larger supply and return pipes going under the road back into the building. So essentially, you save yourself a lot of lateral work. Save yourself a lot of money on the excavation or the underground boring under the road, and then you only have 2 points of connection going into the building there. If you look at the bottom picture, this is an example of all the pipes, all the circuit supply and return pipes going into what is going to be a future mechanical room. So that's it takes a lot of space there. You can see how much excavation occurred, and just the points of connection you're going to have in the mechanical room there. I wrote a nice article back in 2017 that I'd like to share with you guys. After the presentation, but it lists some more of the important reasons about utilizing a vault in your geothermal systems, how to save some money with that, and just make your installation more efficient. Reverse return piping. Kim did an excellent job talking about that, so I'm not going to hammer that home. I would like to leave a little bit more time for Jens with his presentation. But at the very top, you will see a diagram or a circuit detail of a reverse return circuit. So we actually have, I believe this 4-inch coming in on your reverse return. Making your elbow at the, making your turn at the 4-inch 90 there, and then gradually reducing until you get to your inch and a quarter well. The reverse return piping, equal water flow in ground source heat exchange systems circuits equate to balanced heat extraction, rejection to optimize performance of the system. In a reverse return manifold, the first circuit that takes flow in is the last circuit to flow out on the opposite side of the manifold. Also, utilizing balancing valves within the vault can further aid in the balance from the Borefield. So, what Kim had laid out earlier, the balance flow that you achieve with a reverse return piping system, you can further improve that balancing with a balance valve utilized inside the vault. That balance valve will also help you balance the flow from the vault to the building. Utilizing a bypass in piping designs to separate scopes. This is something that I don't see as often as I would like to. A lot of designers and engineers, they get so engrossed with laying out the Borefield, checking all the heating and cooling loads, and they forget about the bypass that goes into the mechanical room. That if you look at the detail up top left, that is essentially what a bypass would look like if you had two larger supply return mains leaving the vault coming into the building. The benefit of having that bypass, it allows you to flush and purge and essentially call the system good even when the building's not up. If the geothermal designer is ready to move on to the next job. By utilizing a bypass, he can essentially close out his scope and hand that building over to the GC or the other trades that are going to be on the job site. Many times you do not see the bypass or the valve in the middle on plans or prints. There's just two vertical pipes coming up for your supply and your return. A contractor will come in and essentially create kind of a makeshift bypass just to achieve that flushing and purging of the system. And then they'll take that back off when they leave. So essentially by incorporating a bypass into your design and your system, that will essentially become a permanent fixture inside your mechanical room. That way, if you ever have any ruptures with the supply or the return between the vault to the building, whether it's a backhoe or someone does some unauthorized digging and severs the line, you're able to essentially shut that off from the rest of the mechanical system, and essentially separate your scope between the Borefield and the internal mechanical system. Utilizing bypass and piping designs to separate scopes. Incorporating a bypass allows the installer to separate scopes at the mechanical room or the vault. Flush and purge the system while bypassing the building. A bypass allows you to isolate the GHX from the mechanical system. If you look at look at the bottom left detail, there's actually a bypass built into this vault. So you can actually further isolate the vault from your mains running back to the building and be able to flush and purge your Borefield without even introducing water into the mains from the vault to the building. All right, the learning assessment. What are some ways utilizing a vault can create more space and reduce excavation costs? How does reverse return piping work, and are balancing valves required in reverse return systems? How do bypasses within a vault or mechanical room work to separate scopes? So the first question, what are some ways utilizing a vault can create more space and reduce excavation costs? Per the example that I showed you in my first slide, essentially you're able to reduce your excavation costs, boring costs from going on the road back to the building. You could also save that valuable mechanical room space for the mechanical contractor, where he can put other equipment in there, or you'd be able to kind of reduce that footprint overall. And if you look in the top left-hand corner there, that's an example of a manifold that's going to go inside the mechanical room. Many projects include these instead of a vault, but it just goes to show you how much space you're actually taking up within that mechanical room. So you're able to kind of turn that back over to the mechanical or the GC. So that's one of the selling features of utilizing a geothermal vault. How does reverse return piping work and/or balancing valves required in reverse return systems? Balancing valves aren't necessarily required depending on the size of your geothermal design or your system. I strongly encourage them, whether you utilize them or not. It's better to have them and not need them, or than need them and not have them. So incorporating those into the reverse circuiting within the vault is a wise decision that helps you balance your Borefield flow from the field to the building. How do bypasses within a vault or mechanical room work to separate scopes? That was what we just spoke about a few minutes ago. It allows you to essentially install that Borefield, install the vault, do flushing and purging, and be able to turn that system back over to the GC or the mechanical and go into your next project. Again, that's just a brief benefit of how a bypass benefits you. Again, if you guys would like more information on that, I'll certainly forward you a more detailed article that I scripted, and lists a lot more benefits of utilizing a geothermal wall and a bypass. Okay. And so I'll go ahead and turn this over to Jens.
Oh, yeah. Thank you, Stuart. We now have Jens Ponikau from Buffalo Geothermal, and he's going to speak to something entirely different, right? So we've learned the reverse return, we learned the European way. Now we're going to discuss a little bit about how we're going to do it within the piping system itself. Jens Ponikau.
Yeah, I guess I'm brought in here to create the controversy, which sometimes we need to innovate, right? And maybe we need to rethink some of the ways we've done things. And so yes, I am from Buffalo Geothermal, and we are design-built company in Buffalo, New York, but we have started to spread out into the New York City and the Hudson Valley market. Work a lot on the affordable housing projects, and I show you a couple examples there and what we've taken along and what we've done. I've never, for the last, I think I put my first geo system in when I was 17, which is about 42 years ago. And back in Germany, as you can tell from my accent. And then I came here and I was wondering why nobody was doing this. So we started Buffalo Geothermal at that time. So we spread out now into larger commercial projects, and we're doing design build from the engineering, from the planning, to every aspect of the system. And we actually guarantee performance, and we actually, one of them called a bluff on me a little bit and said, well, are you willing to put a bond on that? And I said, yes. So we actually bonded the performance of the system for them. It was worth for them. Anyway, so my learning objectives are, understand how heat is transferred in a heat exchanger. And do we really need to have precision there? Or does 10% more and 10% less not really matter so much for heat exchange? So can we build reducing headers? Can we build the systems cheaper? I have never done a reverse return header in my entire 42 years. And can we discuss the benefits to subgroup them? Why do we actually do that? And why do we think it's necessary for it? So, one thing I want to add here. So, I would argue that every loop field is self-balancing to a certain degree. Because if a bore actually has a shorter run, which then has lesser pressure drop, right, because the length is less, then it has more flow. But now the pressure drop, because of the higher flow, goes up in the square function, as we all know. Meaning it very quickly self-balances itself because of that. So all the flow paths will reduce their pressure drop, other ones, and actually, what happens? Lesser flow. Does it mean we have lesser heat exchange? But the pressure drop then also goes down in the square function in the ones who have lesser flow. That means, which will allow more flow then. So that you can actually calculate that. And John Manning in his infamous Dumber Than Rock paper, he assumed, and he said, well, let's assume we have 70% of the pressure drop in the boreholes. Usually it's much, much more. Because we're going, let's say, 1,000 feet of pipe down and up together. And then 30% of the pressure drop is in the horizontal headers, which is usually much, much, much less. But if you do the calculations, that results only in a 10% between around the middle of the pressure drop in terms of flow imbalance. And remember, our ISCO standard allows usually 10% of imbalance. Now, if you actually calculate that, you can see the middle borehole, which is assumed the design pressure drop, the design flow, the furthest away gets about 110%, the other one gets about 92%. Is that now making a difference? Well, keep in mind, how is heat exchange defined? Flow times delta T times a constant. With methanol, it's usually 490. Which also means if I reduce my flow, the water stays in that borehole longer and has more time to pick up heat. So at the end of the day, what is really the difference? And why are we doing then all this? So, John Manning calculated it, and he came up with about maybe a 1 or 2% performance imbalance if we are within 10%. Steve Carbonell actually calculated it, and he said, well, it's actually much less. He actually did this exercise for the new ISCO standard because we had a big discussion there in the group. Shall we mandate reverse return header like it was before? Or shall we mandate a 10% imbalance maximum? And actually, he came up and said, well, I run the numbers, and there's only a total of 0.1 to 0.2% performance difference if we have 10% flow imbalance. We said, why are we even talking about this? We're talking about 1/1000th to 1/500th of it. And what is the potential negative impact of now balancing this more? The time, the cost of running the return header. Increased pumping power. So, as a matter of fact, the committee decided we completely leave it out because we don't want to stuff in innovation. And we don't want to dictate designs that way. So it's not in the standard anymore that you have to have balanced flow. So I'll give you a couple examples. This, for example, is now at one of the NY-GEO buildings, one of the loop fields here. And you see here, we're running it out, 1-2 boreholes, 1.5 inches, and then from here on, it's 2 inches on, and then we header them inside. 10 boreholes, a total of five headers essentially built. And the advantage is that we can now, for purging purposes, control each circuit separately. It's very easy to purge out. We didn't even use a purge card. We used the circulation pumps. It's all about cost saving, material saving, and hours in there. So when we design a bore field, we already think about how do we purge it out. And we want to make sure we have enough flow in there with our pumping solutions that we can easily do that. Number 2, we can always shut them off from the inside. So if, God forbid, somebody with an excavator doesn't check any plans or any piping outside and rips it out, and of course will never happen, but for some reason it always happens, then we can just let the loop field run on 80% of it, and it can sustain that easily for a certain time. So it's resilience, which is also the important part of it. So how is the performance? Well, this is Zero Place. This is a 64,000 square foot building, a multifamily mixed-use building here. And the entire pumping power for this entire building is an average of 400 watts. That's why we pay attention to the pumping power. Because all those buildings are 100% cooling dominated. We're rejecting more heat into the loop field than we're getting out, normally. So we balance them with hot water to cool the loop field nicely in the summertime when we generate all hot water and pull the heat out for that. And the total pumping power at the very peak time at -6 degrees when all the heat pumps were running was 600 watts. 600. So you as engineers, please pay attention to the pumping power. We don't want additional heat in the loop field. Heat is the enemy. So we actually designed the header here. And, there's a case study now. This is probably the most granular monitored geosystem in the world. NY-GEO is monitoring every aspect of it in 1-minute intervals for the last 2 years. And it's quote-unquote the model building for New York State because all the utilities are looking at it and trying to size the grid for it in the future. So we designed actually the whole header here. And you see each individual borehole here, and the entire loop is underneath the building, comes actually in here into the basement, and we can control everything from inside the building. Every single borehole. And it's super easy to pump again. The pumps are enough. These are small pumps. These are about 1.5 kW pumps, but they usually run at 30%, only one pump. It's about this size for the entire building. And they obviously lead a lag. This is all built for resilience. But the reason why we can run such a low pumping power is, again, the design of the loop field for ultra-low pumping needs. Here's the example, performance-wise. So this is the last 12 months of the loop field temperature coming in. So it was about 55 degrees 12 months ago. Then we loaded up. It is our thermal battery in the summertime. We're rejecting all the heat into it. And then over the rest of the year until winter, we're pulling all the heat out again. And magically, that loop field is exactly where it started 12 months ago. Bingo. No balance valves, no reverse or return headers, and ultra-low pumping power. That's what we want. So how does it look in real life when we build something like that? So this is a project we do in Kingston. This is a hotel which has about 82 apartments or built into it, and it has a large indoor pool, and it has a large restaurant associated with it. These are 26 boreholes, and you can see 1, 2 going into a 2-inch header and going into the utility room. 1, 2, going in here, going in. Same concept. Header them inside, because that way we can actually control it nicer. And you have to run the pressure drop. But again, the pressure drop difference here, whether they are 20 feet more or less on one circuit or not, is irrelevant because you're already pumping at 1,000 feet through the ground. So this is how it looks in reality. You see here, sometimes we do elbows here. Depends a little bit on how the driller ended up and the cutting ended up. Sometimes we just put it on top of it, and we come with a 2-inch line here, branch off in 1.5 inches, continue with 1.5 inches to the next borehole. That's it. Simple. And let me ask you this. Are we designing return headers inside the building ever? Sometimes, maybe, or we're not. We don't. We run the pressure drop to each heat pump and make sure we have the correct sizes so they're pretty approximately balanced. Plus, you don't really control what heat pump is on and what is not, and what the flow requirements in that circuit is at that moment. It's not the same. So anyway, just to show you the details, and then of course we embed it into sand and just put a marking tape on top of it so it can be detectable. And here is now another example of a building which has now 60 boreholes. It's a 250 apartment new build in Brooklyn. So we are a little creative in the header design because we have space constraints there. This is underneath the building. This is outside the building. There was kind of a mix there. It was very soft ground. This is why they needed a larger spread footer design. And you can see here, there are 8 boreholes on here, same concept, 1.5 on it, going up to 2 inches, and now they add that all together. Now you go up to 3 inches, and you actually go down here to 4 inches because it picks up those two. It requires that you do pressure drop calculations, and you know that. Here are only 6 boreholes on it, and you can nicely see it only comes in a 3-inch header, and then it reduces to 1.5 inches. The main reason for that is we want to make sure we can push the air out and the debris. So I cannot just make this the same size because then I lose velocity here at the end. So I need to reduce it. But I also don't feel there's a need for any kind of return scenario. It just increases cost for us and time and money. So we tend not to do that. So it's interesting, on this large building, we actually have 2 separate loop fields for 2 different portions of the building because we don't want the long runs. We don't want to have centralized everything. We keep it there because otherwise our pumping power goes up. Remember, pumping is the enemy of efficiency. That's what we're trying to do. So this is the utility room here. You see the 4 headers coming out. We control each circuit. We go to a separated pumping station. So those 2 pumps are doing the loop field. And then those 4 pumps, actually 2 in series, are doing up in the building. Simple. And we can control the pumping speed that way. And the reason why they're in parallel is just for resiliency. One goes down, the other one automatically takes over. And these are ultra efficient pumps. So that is the end of my presentation. Looking forward for the discussion and your questions. Thank you.
Thank you, Jens. Who knew there were so many different ways to do these design, the piping, the horizontal piping? So there's a lot to think about. We're going to open up some questions to the audience to see if we can ask our panelists some questions that I'm sure you've been thinking about throughout this presentation. So if anyone's interested, please raise your hand.
Got to be a couple questions here. Yeah. Could I ask everybody to tell us your name and what organization you were?
Mark Bagden, Labella Associates. With the Swedish, the angled drilling, a couple of questions. One, you pick up more ground. It would seem you more efficient because the boreholes are spaced out further apart. Do you use different sizing programs? You know, do you have a different analysis program to size the well field with angled boreholes than if you assume they were all just 20-foot, you know, on a 20-foot spacing in a vertical orientation?
Yes, so there's a lot of different kind of designing programs. One of the more common used is it's called Earth Energy Designer, and it's not 3D, but basically you would take the middle point of the borehole as the center, so that's the spacing. It's not perfect, but if you design a lot of those systems, you learn how to do it. There is also other programs where you can simulate the whole borehole in 3D, so to say. So,
one other question: is there a range of angles you use, or do you prefer a certain pitch for the angled boreholes?
Typically, we could do from 0 degrees to 15 degrees. You can angle even more, but that's the typical range.
Let me ask the question here. Are you drilling mainly in soft ground or are you drilling in rock?
We're drilling mainly in rock, granite or gneiss, so it's really hard rock.
My name's Jim Thomas Geothermal, and the one thing I noticed on the Swedish design was that the horizontal pipes were insulated. I've often wondered about that, particularly if we're under a blacktop, which tends to be a big solar collector in the summer, can charge up the ground. Seems like maybe insulating the pipes might be a good idea. We don't typically do it here. I don't know if Jens, you have any opinion on that, or Kim, as to whether or not we should be insulating our horizontal runs.
So if you have a lot of pipes running in the same trench, what you could do is to insulate the hot pipe, so to say. So you could insulate every second. Or if you have some spacing between the pipes, it makes a very small difference, but it makes a big difference if all the pipes are packed together, so to say.
Yeah, we protect, underwater, if we run across a sewer line, or if we're running across a water pipe or something like that, we want to certainly protect it from freezing. It depends a little bit on your design temperatures. Again, this is multi-family. Swedish is a different climate. You were probably a little bit more cooling dominated than we are, although I'm not sure in South Sweden how that affects it. But we have, you saw the loop flow temperatures, for example, it runs down to 40 degrees, so I'm not concerned about that, and we actually don't insulate it for that reason. Even if they run really much colder, it depends on how much you're running together in one trench. If you really pack them up, yeah, that becomes a large source of coldness in a certain way. And then certainly that would be a consideration if you know that you're really running down the ground temperature there. But most of the time, it depends on the last header here. We have not yet insulated it because the larger the headers are, the larger the building is, and the more cooling dominated it is, at least in this climate, specifically in New York City and in the climate zones here. Buffalo, New York, a little bit different. But again, we make sure we run in a relatively comfortable range of loop flow temperatures there.
Anybody else?
Absolutely. Brian Posner, NY-GEO Geothermal. Is there a correlation between performance and the distance of the building and the vault when you're doing the vault setup? Is there a certain amount of space that you want the vault from a building? Or is there any sort of correlation there with performance?
You're the vault guy.
Can you repeat the question? I caught about half of that.
Absolutely. Is there a certain amount of distance you want to be away from a building when you're doing the vault, or can it be as close to the building as you want?
Distance really does not come into play. I mean, you can be as far away from the building as you like. That's actually another benefit of having a vault, is you can make your longer runs, from the building or the mechanical room, depending on where your Borefield is located. In terms of being too close to the building, I've seen vaults, as close as 15 to 20 feet from the building. Essentially, in that case, you're basically just trying to relocate your mechanical room, to subsurface. And so, again, just to save more money, more room in the mechanical room, you just, relocating that 20 feet away.
Thank you.
You're welcome.
Rami Gergis, ME Engineering. Interesting in cancelling or removing the reverse return, but how big loop field that you have it without reverse return? If you have 100 well with 10 circuit far from the building, like 900 feet from the building and all that, did you do something like that without a reverse return and prove that it works with no issue? Like, how big is the well field without reversing the return, and you feel comfortable doing with that?
What you saw is that we are building different header sizes for different, how many boreholes are in there, and I would just make the header larger. I would use 4-inch pipe instead of 3-inch pipe, or 6-inch pipe instead of 4-inch pipe to compensate for that, to lower the pressure drop if the loop fit is further away. But I would not then go the extra effort of putting the additional reverse header in there. The reverse header is only for balancing. It is for nothing else. And so I balance it with looking at the pressure drop and making sure my loop field circuits are somewhat balanced, but I don't run a return ladder there. I would just use a larger pipe.
Do you have a balancing valve on the circuit itself?
No, I would never use a balancing valve, because again, for me, the balancing of each individual loop would be too much of a flow obstruction. Plus, have you priced out a 4-inch balancing valve? Just by nature, how they're designed, they have a very high pressure drop. And I don't want that in there. I'd rather have a little unbalanced loop field. And we're talking about, again, not even a 1% difference between the furthest and the closest loop. I don't see a need for it. But again, I don't have a problem with reverse return headers. But for me, it's a cost and effort practice where I rather be done quicker and do another on the job than having this, for me, more complex header design in there. But I do avoid balance valves wherever. I mean, I've never put them anywhere on the source side. There's a potential that you have an inside header configuration, and we again run each pressure drop to each heat pump, and that there is a need to use a ball valve to balance it approximately, to restrict the flow a little bit more. But that's about it. But that is rare. That's maybe 10% of all the heat pumps disseminated throughout the building, where you have to look at the different heat pumps on what the pressure drop is for each individual. So if you go through that effort, again, the balance valves works as good as anything else. Zero place, the entire building, there's 0 balance valves in there.
Thank you.
Mitch Conklin from Geotherm. This question is for Jens. I see that you used a primary secondary pumping setup, and I know that you like to keep your pumps down, or your pump watts down as much as you can. Is that why you went that direction as opposed to just having bigger pumps that were capable of pushing through the building side and the loop field?
No, keep in mind this was actually a relatively large building. This is 250 apartments on there. And so you need a considerable amount of volume. I mean, if you're pumping 250 GPM, the pumps are not the velo pumps here. They don't have the pressure to be able to do that at that velocity at peak times through essentially the loop field and the building. That's really the advantage here, that you can separate them. And the other advantage is if you have a delta peak controller on there, a lot of times in the off season, the building runs in balance, meaning some heat pumps in the heating mode, the other one's on the cooling mode. You don't even need the loop field. And then you just shut off the loop field pumps and save the pumping energy and just let the heat pumps in the building exchange the heat to each other, either cooling or heating. And that, again, it's pushing the limit of efficiency. But again, I just don't want any additional pumping. Keep in mind, all that pumping energy will end up as heat in the loop field.
Yep.
And heat is the enemy.
Okay, thank you.
Maybe one more question if we got it. Okay. And then anybody that wants their credits, please go up to the front corner and sign.
Hey guys, thanks for the talk. I'm Scott from Dandelion. On the subject of head loss and energy pumping power, I was curious, we're not in control of the interior piping necessarily. If MEP is designing it, are there tips and tricks for coaching them to help bring down energy usage with interior pipes and components? Thanks.
It's always a problem. We don't usually bid on other loop field or any kind of jobs if we haven't designed it ourselves. Usually the deal we're making is to say, look, we guarantee our work and we take on the liability for this, but we also, because of that, need to have the control over the design. We work together with MEPs very closely and very nicely, and we explain what we've done and why we've done it. And a lot of them are very susceptible to that. So it's actually a great work together and saying, because we have now the data and the buildings are streaming the data, that we can actually build a case as a backup.
Tracey, you got the last word.
I just want to thank everyone for coming here today. If you have any further questions, I'm certainly sure that the panelists would be happy to meet with you afterwards and have a quick chat. Thank you again, and enjoy the rest of the show. Thank you.